please.
So, good afternoon, everyone. It's my pleasure to have all of you here. Today, I'm going to present the paper, which is a denoising diffusion recommender model, and I'm Jujia, a PhD student from Leiden University. So first, please let me introduce the background of this work. In today's era of information explosion, the internet contains an overwhelming number of users and items. For example, there are 12 million items in Amazon, 2.8 billion users in Facebook, 720,000 hours videos in YouTube every day. So facing with such vast amount of content, many industrial applications use recommender systems to sift through items to offer personalized recommendation for users. Specifically, recommender systems recommends items which are similar to the user's historical feedback, which is also the user historical interactive items. So usually this kind of user feedback using in the recommender systems is implicit feedback, like click and purchase, which cannot strictly reflect users' preference and interest. However, this kind of implicit feedback inevitably contains noises. For example, in e-commerce, a large portion of purchases end up with negative reviews or being returned. This is because implicit interactions are easily affected by the first impression of users and other factors such as caption bias and position bias. Such noisy feedback misguides models in interpreting user preference, thus will hamper the recommendation performance. Therefore, denoising implicit feedback for recommendation becomes an important task. So previous work mainly mitigates the impact of noisy feedback from two perspectives, data cleaning perspective and model perspective. So data cleaning perspective contains two kinds of method. The first one is a resampling method. This method aims to identify noisy interactions and sample more clean interactions for training. And in other words, they just lower the probability for sampling noisy samples. The second one is a reweighting method. It utilizes all training interactions but assign lower weights to potential noisy ones. Notably, these data cleaning methods depend on certain heuristic assumptions, such as the large loss assumption, which is samples with higher losses are more likely to be noisy samples. As their assumptions rely heavily on the distribution of noisy interactions, these data cleaning methods suffer from the limited adaptability, requiring substantial configuration tuning to adapt to different backend models and datasets. And another denoising method is from model perspective. It seeks to enhance the recommender model's inherent noise-resistant capabilities. These model perspective methods usually add random noises to user-item interactions or drop positive interactions as augmented data, and then regulate recommender models to learn the robust representation from the augmented data. However, this model perspective methods solely rely on a denoising model to directly convert noisy data into clean data, imposing substantial demands on the model's representation capability to efficiently capture the noise patterns. So after analyzing existing two kinds of denoising methods, we think it's potentially useful to use diffusion models to denoise the implicit feedback. So diffusion models is a kind of powerful generative model. It can inherently possess a denoising aptitude to enhance the existing model perspective denoising methods. Actually, diffusion models have already revealed remarkable representation capabilities across various domains like image generation and molecular generation. This potential benefit lies in two aspects. The first one is during the forward process, diffusion models enhance the noise diversity by injecting noises with controllable noise scales and steps, potentially leading to the capability to denoise a broader spectrum of noise. And the second one is that in the reverse denoising process, diffusion models decompose the complex denoising problem into multiple steps. Thereby, it can reduce denoising difficulty at each step. In light of this, it's promising to leverage diffusion models to robustify user and item representations from existing recommender model. So to this end, we propose a plug-in diffusion model, denoising models for existing recommender models called the Denoising Diffusion recommender model, which is DDRM. So this is a brief framework of the DDRM. So in the training stage, given the user and item embeddings from any recommender models, DDRM improves their robustness against noisy feedback via forward-reverse progress. So in the forward process, we proactively inject Gaussian noise into the user and item embeddings with adjustable scales and steps using the noisy embeddings. And then the reverse denoising process then iteratively remove noises via learnable neural network. And then during the inference phase, given a user DDRM, you should choose a starting point to initialize this refined forward-reverse process, thereby generating an ideal item that aligns closely with the user's preference. So to achieve the denoising target with the DDRM, there are two key factors. The first one is we need to offer the appropriate guidance to steer the reverse denoising process. The second one is providing a proper starting point to start the forward-reverse process during inference phase. So in other words, the denoising process hinges critically on two elements, the direction of denoising and the starting point. As for the guidance in the denoising process, our goal is to derive effective representations from weak collaborative informations, which helps to guide the denoising process towards the clean embeddings of users or items. As for the starting point, we aim to incorporate personalized information rather than relying solely on the pure noise. This strategy diverges from traditional diffusion models, actually, which typically generates the image from pure noise guided by abundant textual instructions. But in the recommendation scenario, guidance through collaborative information is not as explicit as the textual instructions, so it makes it challenging to generate personalized ideal items if we just use pure noise as a starting point. So by incorporating personalized information, it's more likely to generate the ideal item closely aligned with individual user preference. And then I will talk about our detailed method. So first, in the forward process of the training phase, given pre-trained user embeddings EU of user U and item embeddings EI of item I from a backend recommender model, we begin the forward process by setting EU0 equals to the EU and EI0 equals to the EI. Subsequently, we continuously incorporate Gaussian noise into EU0 and EI0 separately with adjustable scales and steps where alpha T controls the noise scale added to the embedding in the current step. So to regulate the noise level in each step, we employ a kind of linear variance noise schedule in the forward press. And after getting the noisy user embeddings EUT and the noisy item embeddings EIT in the forward process, we denoise its embeddings iteratively in the reverse process until we get the final EU0 and EI0. In each reverse step, we design the user denoising module and the item denoising module to denoise the user embeddings and item embeddings separately, since the noise distribution is different for users and items. Specifically, to ensure the tractability in the embedding denoising process, it's paramount to utilize specific conditions as guidance. In this context, DDRM incorporates two key conditions during the denoising phase, which are the collaborative information and step information. So collaborative information, which is based on the user interaction behavior, it can enable the denoising module to recognize user preference, subsequently assisting to identify and mitigate noise. Additionally, the step information also affects the denoising process. It provides insight into the current noise level in the embeddings, so it can offer a gauge in the extent of denoising required at each step. Therefore, we use collaborative information, CU, and step information as condition elements to get the reconstruction process in the denoising module. And then in the inference phase, we need to apply the refined forward-reverse process to a starting point, and thereby generating the ideal item to do the recommendation task for each user. Since guidance through collaborative information is not as explicit as textual instruction used in field like image generation, we incorporate personalized information into the starting point rather than using pure noise. Particularly, we take the average embeddings of users' historical liked items as the input, since the interaction information reflects the preference of users. Thereby, it's more likely to align the generated ideal item closely with the individual user's need. Given the embeddings of the generated item, we then present a rounding function to ground the generated item to the existing item candidates by the embedding similarity. And the next part is the experiment part. So to demonstrate the efficiency of our proposed DDRM in the denoising implicit feedback, we compare DDRM with some sort of model agnostic denoising method like TCE, RCE, DCA, and BOD. Furthermore, we also compare DDRM with other competitive baselines, including model perspective denoising methods and generative methods. So we can say that DDRM mostly outperforms backend models and other model-agnostic denoising methods across all three datasets. And the next experiment is about random noisy training. Actually, we train our model in the dataset with different noise ratio, and the result shows that our proposed method consistently outperformed both the backend model and the denoising method. And also, as the noise ratio increases, there is an overall declining trend in the performance of all the model. And we also do the inference step analysis experiment. Actually, we change the inference step to say the performance and the cost. The result shows that the optimal performance can be achieved with fewer than 100 diffusion steps. This actually contrasts with traditional diffusion models commonly employed in the generative tasks because they also often require up to 1,000 steps. This is because these traditional models aim to reverse from pure noise during the inference, which may need more steps to reverse in order to get the high-quality image. But for our DDRM, we start with embeddings that already contains the personalized information which reflects the user preference. So we need fewer steps to reverse compared with the traditional methods, which also saves the computation time cost. And we also do some design variation to make sure the model structure and method of our method works well. So first, we change the architecture to the transformer. We can see that the performance is not as good as our proposed method. We think that this is because the inductive bias introduced by the addition model structures in the transformer, which may be inappropriate in the denoising context, thus rendering suboptimal performance in reconstructing these embeddings. And for other variation experiments, if you are interested, you can see our paper. And the final part is the takeaways. So we propose a model-agnostic denoising diffusion recommender models, which robustifies the user and item representations from any recommender models against noisy feedback. And there are some future directions might need to be explored. The first one is that we can enrich the denoising module with more well-designed neural network. The second is that we can explore adapt DDRI for a broader range of recommendation tasks. And this is my presentation. Thanks for listening. I'm open for any questions. Thank you.